Screen visible, right, ma'am? Shall we continue, ma'am? Shall we start? Or wait for some more people? 82. Screen visible, ma'am? Ramesh, shall I start? I'm unable to hear, I think, from anyone. Are you there? Am I audible?
Can you hear us, sir? Hello?
Yeah, I'm able to hear.
Oh, okay, sir. Yeah, we can start. We didn't say anything because we thought you couldn't hear us.
Okay. Now, you are, am I audible, right, to you? Okay, fine.
Yes, sir.
Screen visible?
Yes, sir. Yes.
Okay. There's 12 participants are there. And some more people to come. Today alone, last hour may not come, I think, because I'm having some meeting. For today, you take a rest. We can compensate that class in some other time. Okay. So we'll start today's class. Okay. So we saw how when the ash layer is controlling the expression for the time for the, a particular conversion or time as the radius is decreasing is this particular thing, right? This is for the ash. Otherwise, we can go for here, I think. Yeah, I'm just running through. I'll come back again. Yeah, here. Still, people didn't come. So here we are thinking about the spherical sphere where xp is 1 minus rc by r whole cube, where rc is the radius of the unreacted core and capital R is the radius of the particle. So there are three diffusions or resistance. One is film diffusion, ash diffusion, and reaction control. Reaction resistance. So for a spherical particle, this is shrinking core model. The size is not being changed. So T by tau is xb. for a film diffusion, whereas for a ash diffusion, T by tau is 1 minus 3 times 1 minus xb whole power 2 by 3 plus 2 into 1 minus xb. I told you how to remember this. 1 plus 2 is 3, therefore minus 3, right? So this is xb, 1 minus xb. In all the expressions, it comes as 1 minus xb. This is 1 minus xb whole power 1, 1 minus xb whole power 2 by 3, right? So that's how you try to remember it. This is 2 and this is 3, right? That's why 2 by 3. And reaction control T by tau is 1 minus 1 minus xb whole power 1 3, right? So these three you have to remember somehow. Then when you put RC by R, XB as RC by R, and for a complete conversion, you can put as RC is 0. When RC becomes 0, then what will happen? The entire expressions comes to tau is this particular thing, right? Rho B R divided by 3B Kg CAG, and in ash diffusion, it is tau is rho B R squared 6B DE CAG, and for reaction control, tau is rho B R divided by B K prime CAG, right? CAG, right? So here you can see the difference between all that thing. This is B, B, B. In that here it is 3 is there, here 6 is there, and here B is there, right? So sorry, no coefficient. So 3, 6, no coefficient. Rho B is common for all. R for film diffusion and reaction is R alone, whereas ash resistance it will be square. One more thing which is different is the same thing is CAG, CAG, CAG. But the different is gas is mass transfer coefficient, gas mass transfer coefficient. Ash, you get DE, that is the diffusion, effective diffusion we call. And reaction, you get K prime, that is nothing but the rate constant. So, based on what is controlling, depending on that, you will put down whatever is the coefficient. If there is a film diffusion, you get Kg. If there is a ash diffusion, you get DE. If there is a reaction, then you get K prime, that is the rate constant. So this is for a spherical particle if the size is not changing. Like that you can do for a cylinder also, except cylinder volume will be different. So when the volume is different, you get accordingly, right? So rest of the procedure is same. Volume is nothing but earlier for a sphere, you are getting as 4 by 3 4 pi r cube for volume. And if you differentiate dV, then 4 by 3 pi r square into dr you get. One second. Let me. One second. Let me. There is one more meeting which is going. Am I audible now? Am I audible?
Yes, sir.
Okay. Because the other meeting, I think it is. You are not able to hear the other meeting, right? You are hearing it any sound?
No, sir. No, sir.
Okay. Because I'm simultaneously on one more. Yeah. Here. Why is not going for a screen sharing? Yeah, this is right. Yeah, spherical. We are assuming it is like this, right? Okay. If it is a constant size particles, it is like this, right? So I told you how to remember, right? For a cylinder, the volume will be 4 pi r square L, right? So based on that, the dV will change. Accordingly, the expressions also will change. I think I'm getting disturbance. Let me cut this thing. Don't want. Yeah, I stopped that because I'm getting too much of disturbance. Yeah, spherical, right? So if the size is not changing, then this will be the expressions. For a cylinder, you get these expressions. The derivation is not required, but if the derivation is required also, it is same like that, except the volume. Volume is 4 pi r square L will come, whereas for this 4 pi r cube will come, right? So dV will change for this and this. Accordingly, you can see here 4 you get, here you get 3, here 2 you are getting, here it is 3, because 4 by 3 pi r cube, right? So here 5 pi r square, so only square will come, right? That's how you remember. Rest of the thing is same. K prime, D, kg, rho b, square. This square, everything is same, except only the volume will change, right? So you can use for a flat plate also. Flat plate XB or L, we call it as a thickness, half the thickness. 2L is the thickness, half the thickness. Again, the expressions are same. Expressions are same, except here instead of R, you get L. And accordingly, the coefficients will change, because here also dV, volume will change, right? So here it is square, here it is square, L square you get, right? So for a flat plate, you get L, that is the thickness. 2L is the thickness we call. L is the half the thickness, that is thickness by 2. Why we use the half the thickness L? Because 2L, because we use a symmetry, just like a spherical particle, we use a symmetry for this. Okay. So these derivations are not that important, but just since the expressions are here, I'm just giving here, right? The other thing, what is more important is if the particle is not constant size. If the particle is not a constant size, if the size is changing, then still we have to get what will be the expression for a film control, what will be the expression for ash control, what will be the expression for a reaction control. Further, what we have to do, we'll see now, right? So rate of a reaction for a shrinking surface, if the particle is changing, right? Earlier we saw constant size, but say the size will change, right? If the ash is removed, then what will happen? The diffusion through the ash layer may not be present. Therefore, the size will change, right? So whenever we are talking about if there is a changing in particle size, what we mean by that is there is no ash form. When there is no ash form, there won't be any resistance at all, because there will have only two resistances. One is the gas resistance, the other one is the reaction resistance. There is no ash resistance because ash layer is being removed, right? So when no ash forms, as in the burning of pure carbon in air, the reacting particle shrinks during the reaction. Finally, out of the 5 steps, what steps we are having? One is diffusion of reactant A. A is gas from the main gas body to the gas film, then the reaction, and third one is diffusion of the reaction products. If there is no changing and the ash is being formed, 5 steps will come, because again going through the ash and again coming back through the ash. Since we are assuming that since there is a change in particle size, that means no ash is formed. Ash is formed. As soon as the ash is formed, it is being removed, right? So there is no diffusion there. Therefore, 3 steps will be there. Out of the 3 steps, first one is diffusion of the reactant, and third one is diffusion of the products, right? So first two only we take, that is diffusion of the gas phase and the reaction, right? So hence the rate controlling step may be only 2 instead of 3. So either it is a gas film or a reaction control, whereas no ash film will be formed. So when there is a chemical reaction, what is happening, right? When there is a chemical reaction, what is happening? The expressions derived for the single particle of unchanging size are directly applicable to the shrinking surface. For a chemical reaction control, whether the particle is changing its size or not changing its size, the same expressions can be used, right? But diffusion through a gas film, when the diffusion through a gas film, you can see the diffusion, since the particle is reduced, the size of the particle or the gas which is being wetted by this particular thing will change. Accordingly, the values will change, right? So the changing of the particle size in turn changes the film resistance. The film resistance at the surface of the particle depends on, because so film resistance is on the surface of the particle. As the particle shrinks, the surface area is getting reduced. Therefore, the area which is being wetted by the gas is also changing, right? Therefore, the gas film resistance will have different values. Whereas the reaction is occurring on the surface, therefore the reaction things will have the same, the expressions, right? So here one important thing is the film resistance at the surface. How much the film resistance depends on the following factors. One is the relative velocity between the particle and the fluid. What does that mean? Relative velocity of the particle and the fluid. Second one is particle size. Third one is the fluid properties. Fluid properties, you know what are the fluid properties. Particle size is nothing but the radius. But what is this relative velocity between the particle and the fluid? That is nothing but the particle is reducing with respect to the time. Not only that, the gas is being diffused. So how much the solid is being reduced and at what speed the gas is being diffused, that is what is the relative between the relative velocity between the particle and the fluid. So we take one assumption that we call it as a pseudo steady state assumption. That is, the rate at which the solid is being decreased is equal to the rate at which the gas is being going onto the surface. So if we make that assumption, actually it may not be true, because gas diffuses much faster than the size of the particle reducing. But still, if you're not making that assumption, you cannot get the expression. So we make one pseudo assumption that the gas which is being going at what speed the gas is going, the same speed the particle is being reduced in the size, right? We use that. Then here some mass transfer equations will come. One mass transfer equation which is very popular is called as this Frost-Link correlation, because here two important things are there. One is the gas is moving. Not only the gas, even the solid is moving. That is, the core is moving. Whereas in the previous cases, what we assume, the size is not changing, but here the size is changing. The ash is not being formed, right? Therefore, we assume there will be a correlations between that. The correlation for mass transfer of a component with a mole fraction of Y of the gas in a fluid to a free falling solid. This is the expression kg. dP is the diameter of the particle. Y is the mole fraction divided by diameter. Is 2 plus 0.6 Reynolds number half, Smith number 1/3. This is a correlation which was given by Frosling, right? It's a very popular correlation. This correlation, it even comes in heat transfer, especially when there is external flow heat transfer over a spherical surface. I don't know whether in heat transfer you got this expression or not. 2 plus something you get. The 2 is very important there, right? So where Smith number is mu by rho d, the d is the diffusive, not diameter. dE is the diffusive, right? Effective diffusive. Reynolds number is dV rho by mu, right? So if you substitute these two, then these expressions will come. This relationship is called as the Frosling expression, which gives the relations of the kg with the d. That is the what do you call diffusion, right? So here during the reaction, a particle size changes in size. Hence kg changes because the particle is changing in size. Therefore kg changes. So kg rise for an increase in gas velocity. So we assume that the particle is small and the diameter velocity is less. Your kg is directly proportional to 1 by dP. This is some assumptions you make to make the expression simple, right? If the particle is large, we assume that kg is a function of u power half and dp power half. You can ask me how you are getting these expressions. A lot of scientists might have done some experiments and then found that from the experimental results, the kg is indirectly proportional to the dp, diameter of the particle. If the diameter of the particle is small, your kg is more. If the diameter of the particle is large, initially, the kg will be less, right? So kg, if the particle is large, this is how, in one more factor it will depend, that is the velocity. So this equation 3, one more important thing is, this equation is valid only for a Stokes law regime. You know what is a Stokes law? The Reynolds number should be less than a particular value. In this particular thing, the Reynolds number is around 0.3, less than 0.3. So this derivation is not required for you, but I gave here in the slide. If you can follow, you follow. Otherwise, no need of this derivation, right? But final form is required, right? So again, dNB, you are substituting NB as rho B into V. Again, the same thing, 4 by 3 pi r square. Here you are writing in terms of the surface area, external surface area. So 1 by 4 pi r square, you are substituting it. Same like the previous one. This is for the Stokes regime. So here one Stokes regime, we discussed that kg is 1 by dp. So 2d by dp, if you, because 2 is there before. So 2d is nothing but dp. dp is the diameter of the particle. D is the what is this? Diffusivity. So capital D, small d. Small d is diameter. Capital D is diffusivity. dp is nothing but 2r. Because 2 radius, so 2 gets cancels. So kg you can write as d by r for a Stokes regime. So if you substitute kg as that and then take the limits, the final form of the equation is like this: rho b r square 2b cag d into 1 minus r by r naught whole square. Expressions almost look similar, except here the particle size is changing, whereas the previous one, the particle size is not changing. So for a complete conversion, you can write as r is 0. Therefore, initial, it depends on what is initial, what you are taking. So r naught is the initial, that is what I is taking. Therefore, r is any radius at any particular time. You can write t by tau. Like that, you can do the fractional conversion. 1 minus xb is r by r naught whole cube. So this will be the expression for the gas film resistance. 1 minus xp whole power 2 by 3, right? This is the expression which you got for the reaction, am I right? In the what do you call, when the particle is not changing, right? So this expression is for a particle change. Again, there is one more catch in this. The approximation for this is it is following a Stokes law regime, right? This equation is well represented for burning of solid particles, burning of liquid droplets, or whatever it is. Okay. So like that, cylinder particles also you can write. Cylinder particles, earlier itself I told it is only the diameter, what is that? Volume will change. So based on that, you see that expressions. I didn't give you the derivation here. You can do that because 4 pi r square L will be the volume. You change the volume accordingly here. That this particular thing will change, right? Dr, where you put D at B, this value will change accordingly. The entire what do you call this? Integrations will change. So not much of required that derivations. If you want, you can go through it. So this is the final expressions. For a spherical particle is this, cylinder, this, and even for a shrinking particle, again, shrinking particle, small particle, and large particle. Small particle, the expression is this. The expression is this. This absolutely, you can see here, the absolutely same as this particular thing. For a particle shrinking size, particle is shrinking or particle is not shrinking, the reaction control is same. Reaction, the expression is same, tau. Tau is same. Whereas T by tau will have differently. Here it is 1 minus xb. Here you get 1 minus xb whole power 1/3. Sorry. The expressions is same. I am comparing this. You should compare these two. Yeah, sorry. This expression is same. Only this expression will change. This expression will change. Now, one more catch is for this particular thing, for a particle which is shrinking, film diffusion and reaction control, the expression is same except here 1/3 is there, here 2/3 is there. Okay, that somehow you remember. The rest of the thing is same. Here R is coming, R square. Here is same. Film diffusion, you get only R. Here you are getting R square. Ash diffusion, it is not applicable because ash is not present at all. Only two resistances will be there. Okay. So I complete this derivations. Please do these derivations in the afternoon's class, right? And then we have to do the problems, right? That problems, these are the set of problems, 4 problems I think I gave. Yeah, 5 problems, 6 problems I gave. All the 6 problems, definitely they will come in the exam, at least one. So for this problems, what I did is in our LMS, I put as unit 2 problems of a Gavane book. Please go through that problems, the same, whatever problems I gave here, the solutions I gave there. Go through the problems in the afternoon's class. Afternoon, I may not be coming here. Vignesh, you are there? Yeah, Vignesh. Vignesh is not there. Harshita, you are there, Vignesh?
Hello, sir.
Yeah.
Hi, sir. I'm here, sir.
So one thing I want you to do is in the afternoon's class, you start our Teams class, right? And then record, and then try to go at least the first problem you do. You see the solution in the Gavane book. Already it was put in LMS, right? So you start the class and record it. Try to just run through that what do you call solution. And anyhow, I'll next class I'll take it, but last hour you can take it. Okay, and then send me the attendance. Okay, ma? Any doubt,
Yeah.
no? So you understood what I told? These 6 problems, I gave the solution in the LMS site, unit 2 problems. So at least one problem you can take. I think this problem you can take, first problem. Right. You take the first problem and see the solution and start telling that solution to the class and then record and then send me. Okay. Either it is Zoom. I think it is better Teams. Teams is better. The same thing. Okay.
Okay.
So I
Sir,
stop
do you
here.
have to share that answer in the
What?
like? Do you have to share the screen of that answer in the Teams meeting, or I'll just on the meeting and all them will
Yeah, I
solve it
share
and
the
I'll record it
because
and
you
I'll
have to
get
share.
that
No?
link
You have
and
to download that LMS whatever I put and then start discussing about it.
yeah. Oh,
Okay.
okay, sir. Yes, sir.
Solution, discuss about it. If any difficulties are there, let me know what is the difficulty. Then I'll try to rectify. One or two problems you can do. That depends on the time, on your interest. Okay. Try. Anyhow, I'll again take it. Okay. So I'll stop here. I'm having some work already. I'm delayed. That is why I started a bit before. Okay. We'll meet in the next class. That is tomorrow. Okay. Thank you.
Thank you, sir.
Thank you, sir.